So now we're going to evaluate the various Java programming paradigms that we've covered in this course, and ideally you've learned about in other courses that you've taken, just so you can get a comprehensive perspective on different ways of programming with Java. So we're going to cover the classic object-oriented programming style, including the very modern Java structured concurrency enhancements to classic object-oriented programming. And then we're going to talk about synchronous and asynchronous functional programming and reactive programming. So we're going to compare reactive programming with all these other approaches. So as you can see here, there's a nice fourfold chart, sort of a quad chart, where we can have an X and a Y axis, where the Y axis has either methods that return a single value or some kind of stream that returns multiple values. So that's one dimension of comparison. And then the other, which is the X axis, is synchronous versus asynchronous. Does the caller block until the call is done, or does the caller not block until the call is done? So those are the ways we're going to kind of classify this space. If we think about your grandfather's Java, or your grandmother's Java, depending on who programmed in your family, we had object-oriented programming since the early to mid-90s, and these are traditional blocking operations that return one value. The good part is that it's simple, the error handling is straightforward. The downside is that they can be inefficient, may not be suitable for long duration operations because the thread of control is blocked, which can cause all kinds of problems. Here's a very simple example, which you can see in my live lessons GitHub repository for an interesting example called the image stream gang case study, where we have a method called download content that takes a URL. We synchronously open that URL, get back an input stream, and then we go into a for loop that reads from that input stream a buffer at a time and writes it to an output buffer. And so all those calls are synchronous. It's just classic object-oriented 101 kinds of things. Now, what's interesting is very modern Java, with its support of structured concurrency and virtual threads, are actually making synchronous object-oriented programming cool again. So it had kind of fallen out of favor for a long time, but now it's back with a vengeance, and you can do all kinds of interesting things with structured concurrency and virtual threads and blocking operations, because blocking now is very, very lightweight in very modern Java. So this is kind of interesting. It's kind of like fashion. If you wait long enough, then your wide ties will come back in favor and your bell-bottom jeans will come back in favor, just because these things tend to go through cycles. So this is an example of a cycle. Taking another look at a different paradigm, we have synchronous programs that have multiple values. And this, of course, is where Java Streams lives. And this enables functional style operations on streams of elements. The good part is that you can have these elegant ways of streaming together various intermediate and terminal operations, which allows you to compose things together in a nice functional way. You can use collections, both as the input and the outputs of these things. And it's also good for both CPU and IO-bound tasks if you know what you're doing and use your managed blocker mechanisms properly. The downside is it's not really parallel unless you say parallel stream, which, by the way, is not the very hard thing to do. And the calls are still blocking. So again, not the end of the world, but you're going to have to learn how to use things like managed blocker to make this scale up properly, especially for IO-bound tasks. Here's a very simple example also from the image stream gang case study, where we make a call to get input to get a list of URLs. We turn that list of URLs into a parallel stream of URLs. We get rid of anything that's been downloaded and cached previously, so we ignore those because we don't want to have to do them again. And then we download each image synchronously. We apply a bunch of filters to each image synchronously, but in a pool of threads, of course. And then we convert the results to a list of images. So for my money, this is usually the simplest way to program and often runs pretty efficiently. But there's more. So another way to do things is by using this futures or promises-like approach involved with the completable future framework. And this has single value return from the methods in completable future, but the operations are run asynchronously. So the good part of this is it's non-blocking, It can improve performance for IO-bound tasks, often one of the most efficient ways of doing things. It's very, very lightweight, very optimized. The downside, of course, is that the control flow is a bit complicated if you're not well-versed in asynchronous programming, and error handling can be a bit complicated unless you understand the patterns for doing error handling in asynchronous programs. Again, not the hardest thing in the world to learn, but a lot of people really have had a hard time getting their head around this particular model. I love it, but a lot of people wrestle with it. Here's an example, which you can see in this code base, where we're going to reduce a big fraction asynchronously, and then we're going to take the results of that when it's done, and we're going to convert that reduced improper fraction to a mixed fraction, and then we're going to go ahead and print it out. So just a very simple example, again, available in my GitHub repository. Now, there's also a hybrid model that combines Java streams, especially Java sequential streams, with the Java completable futures framework. And this hybrid model starts really getting us into the zone, the quadrant of reactive programming, sort of as it's intended to be used, where you've got asynchronous operations that are streamed. The good part is you can improve performance because we're using completable futures, and you can also have a nice structured flow of control because we're using sequential streams. The downside is error handling is a little complicated again, and people tend to lose their minds with debugging this due to the mixture of paradigms that, while capable of being integrated, are a little trickier because they didn't really start out intending to be integrated. And here's an example, again, from my image stream gang case study where we get input, we get a list of URLs, we turn it into a sequential stream of URLs, and then we apply the map operations to basically asynchronously check and see if something's been downloaded already and cached. For things that are not downloaded and cached already, we asynchronously download them. Once they're finished downloading, we asynchronously filter them to do data transformations on the contents of the images. We collect those into a single completable future. And when everything is done running asynchronously, we then go ahead and log the results. So that's how you can combine these things. Not for the faint of heart, but once you get the hang of it, it's pretty cool. The fourth or fifth, I guess it is, and final model here are the reactive streams programming, like we get with Project Reactor or RxJava, where this idea of asynchronous multi-valued semantics are baked into the API as first-class citizens. So you get non-blocking back pressure, composability, very powerful concurrency and parallelism model. The downside is you've got to figure out this API, and some people struggle with that, although, again, I think it's pretty cool and fun to learn. Here's an example that we would use where we're going to take a list of URLs, we're going to download a bunch of things in parallel using something called a parallel flux, and we're going to run that on a parallel scheduler that works for I/O, and then we're going to map, and by downloading and storing images as part of this reactive stream in a parallel flux, we convert the parallel flux back to a sequential flux, collect the results into a list, and then we block until we're all done. So pretty cool model, not that much more complicated to look at than the parallel streams approach that we looked at back over here. Although, honestly, I think the parallel streams approach is a little bit cleaner, but nevertheless, this is what you get with reactive streams. Plus, there's lots of other things you can do with the reactive streams that you can't easily do with parallel streams. So that's the end of our discussion of Java programming paradigms, ranging from classic object-oriented programming to modern or very modern Java structured concurrency on one hand, and then various forms of functional programming and reactive programming and everything in between.